Hello, everybody. So nice to talk to you again today. It's Professor Rehse. I'm a University of Windsor physics professor, and I am thrilled to be talking to you all from beautiful, sunny Windsor, Ontario, Canada. We are talking to each other on our fall or autumn Halloween special edition of our DoD STEM K-12 talks. And we have a really interesting topic for you today that's actually motivated by a talk that we had at our last learning session. So I just think this likes to kind of illustrate how things in physics, you can get inspired by almost anything. So we were sitting through a bunch of talks last month and heard this really fascinating talk about a big ship. And that made me think, geez, I want to learn more about that. And that's the way you guys can do it too with physics. Anything around you, if you don't understand it, that's an excuse to just jump right in, just learn something more. If you didn't know anything about it, that's fine. By the time you're done, you're going to be a way better educated person than you were before. So it's just fun to be able to just investigate things and you don't even necessarily know where it's going to take you. So let's go ahead and jump right into this topic that was inspired by a talk that we heard last time. So I'm going to share my screen here and let's bring this up. So here it is. All right. So I call this 68,000 tons afloat. What's up with that? This is going to be a study in buoyancy. So this talk we're going to see is going to be a very Great Lakes oriented talk. Because it's a Great Lakes oriented talk, we have to start with our traditional land acknowledgement statement. So the University of Windsor does sit on the traditional territory of the Three Fires Confederacy, the First Nations. And this includes the Ojibwe, the Ottawa, and the Potawatomi. We respect the long-standing relationships with First Nations people in this place and the 100-mile Windsor-Essex Peninsula and the Straits of Le Detroit of Detroit. So this is a beautiful area to be in. We're surrounded by the Great Lakes, and this talk today kind of has a little bit of a Great Lakes flavor to it. So specifically, I was motivated by Grayling Mercer's September 25th talk. So Grayling runs the Hoffman Planetarium over on the other side of the river there in Michigan. And for those of you who didn't see that talk, Mr. Mercer was visiting with the Army Corps of Engineers, and Mr. Sherrod was a person shown on the right side of your screen here that he ran into, and they were talking about the largest ship to pass through the Soo Locks. So Mr. Mercer was talking about the Great Lakes and how big ships move on the Soo Locks. And while he was there visiting it and filming, and he showed us this, he ran into this man, Mr. Sherrod, who was actually an expert on the ships moving through the locks. And while they were there, there's this ship in the background here that you see here. It's called the Paul R. Tregartha. And the Paul R. Tregartha is the largest ship to pass through the locks on the Great Lakes, one of these giant Great Lakes cruisers that carries massive amounts of cargo, coal and iron and ore and things like that from one end of the Great Lakes to the other. This thing carries 68,000 tons of cargo capacity. 68,000 tons. That's a lot of cargo. So when they were talking about that, I was listening to those talks just like you all were, and my response was 68,000 tons. Whoa! Mind blown. 68,000 tons, and it just floats across the waves like that. How is that possible? That is so much mass. How is it possible that these things can get from one point to another, to weigh so much, to have so much mass, and to just be an easygoing lake cruising vessel? When you think about it, it just makes your mind explode like this little animation guy over here. So I started to ask myself, how does something that big even float? Maybe you guys have wondered that before. It's a different question. Sometimes we ask how those big planes fly. Sometimes you think, how do those really big ships float? How do they do that? So I wanted to learn more about that. Ooh, there's something that just goes down like that, right? But these ships don't, they float. So how does that float? Let's dig into it. The answer is going to have something to do with the idea and the word that we call buoyancy. So that's going to be our goal for today, to understand buoyancy, because that's going to be the answer to how something that big can float. So buoyancy describes why, here's this great picture of two bowling balls. They're the same size. Buoyancy is going to tell us why some things sink, like this white bowling ball here, and some things float, like this blue bowling ball here. They are almost exactly the same, not quite the same. And the difference is going to be why one of them sinks and one of them floats. And buoyancy is going to be the answer to that. So if we can explain what's going on with these two bowling balls, why one of them is sinking and one of them is floating, then we're going to be able to explain the ship. So physicists love to do this too. The ship is complicated. Let's start with something simple like this bowling ball. You can see the example in front of you. They look the same, but one sinks, one floats. Why? If we can explain that, which is quite simple, then you'll understand the ship, which is not so simple. Physics at its most powerful. That's the way to get at the truth of matter. So let's talk about buoyancy. Let's dive into this. How do we explain buoyancy? Well, to understand buoyancy, which is going to be the explanation and the key idea of our little chat together today, we're going to have to understand two key concepts, two ideas. And those ideas are going to be density and displacement, two D words. So I guess we are sponsored by the letter D today, density and displacement. We're going to have to understand those two ideas and those two properties. So let's start with the first one, density. What is density? Okay, so to understand density, all objects that have matter in them, that is, they weigh something, they have mass, they're composed of atoms. All things that are matter objects have these two very important properties. And these two you probably know. One is called mass, all right? Mass is the measurement of mass of an object is the measurement of how much matter it contains. Literally, how many atoms or molecules are all jammed in there. It's the amount of matter that's in it. And in Canada, so when we buy fruit and there's a scale and you would buy a kilogram of fruit, and that's a measurement of mass. And on every container that you buy, it'll say kilograms on the outside of the box. That's a measurement of mass. It's a little bit different in the United States where you use weight. And so we're not going to dive too far into this today, but it's important to know that mass and weight do have different definitions. So here's a picture of an astronaut on the Earth and an astronaut on the moon. An astronaut's mass is 120 kilograms, and that does not change no matter where that astronaut goes. Mass is just how much stuff is composing the thing. And an astronaut just has this many atoms, this much stuff. So that astronaut's mass is 120 kilograms, no matter if the astronaut's on Earth or on the moon. But the astronaut's weight, which is what confuses the matter just a little bit, because in America, when you go to the grocery store, you buy things in pounds. Well, pounds is not mass. Pounds is a unit of weight, actually. So on Earth, this astronaut's weight would be, say, 1,200 newtons. That's the measurement of weight. And this astronaut's weight on the moon would be a sixth of that, or 200 newtons. So we all know you're like weightless in space, or you weigh a sixth as much on the moon. That's the weight. But the mass does not ever change. So your mass is constant because it's just the sum of all the stuff that's inside of you. The other property that all things have, so we said one was mass, is everything that's a material object has volume. So they have mass and they have volume. Well, volume, the volume of an object is a measurement of how much space all that stuff occupies, right? So I have mass. There's a bunch of atoms and molecules that make me up. So I definitely have a definite mass, but I also have a finite volume because it takes physical three-dimensional space to cram all that matter in. All right, that's called your volume. And the units of that would be something like liters or cubic meters or cubic centimeters, which is what a cc when you get an injection is, right? And then when you start taking classes, you're gonna learn all these equations for calculating the volume of regular objects, like the volume of a sphere, the volume of a cube, or the volume of a rectangular prism or a cylinder, or et cetera. We're not gonna need any of those equations today, but the volume is the three-dimensional space that object occupies, mass and volume. All right, so here's just summarizing. Every object has mass and every object has some volume, and here's how they were defined. Well, then simply put, the density is just a simple ratio or quotient of those two. It's the mass of the thing divided by the volume that it occupies, right? So it's its mass divided by its volume. And so if units of mass are like grams or kilograms or something like that, then the units of density are usually given in kilograms per cubic meter. But it could also be something like grams per cubic centimeter or something like that. So it's a mass per unit volume, but kilograms per cubic meter will be okay for us now. And that's a really simple calculation. You guys can all do that. It's not going to get any more complicated than that. It's just a division of mass by volume, and that defines what an object's density is. So the density of the object is its mass divided by its volume. So things with a low density have very little mass crammed into a volume. It's like a helium balloon. Everybody knows helium balloons, right? Well, we're going to see that helium balloons rise up in the air because they have such low density. So the helium balloon can be pretty big. Its volume is big, but there's very little mass. So the mass is small up in the top part of that ratio. So the density is small. And so we'd say, oh, a helium balloon's not very dense at all. There's just not a lot of mass in this big, big volume. Something that has a high density will have a lot of mass crammed into that same volume, or maybe even a smaller volume, like a lead brick, a heavy lead brick, or a brick of gold. Really, it's small, but it's really heavy because it's a lot of mass and it's all crammed into the small volume. That's a high density object, right? The mass is high, maybe the volume is small, so its mass per unit volume is actually pretty big. All right, so be thinking of that conceptually of what density is. Now, importantly, water has a very easy to remember density of 1 gram per milliliter, or 1 kilogram per liter. So let's try to remember that. That'll be a useful number to kind of remember. Water is just 1 kilogram per liter. Makes it really, really easy to do calculations of buoyancy when you're talking about floating on water. That makes it really easy. All right. So I said we're still trying to explain buoyancy. Follow with me along in the argument. So we just explained density. Now let's see if we can explain displacement, the other D word for today. What is displacement? Well, here is a nice picture that illustrates the idea of displacement, but you guys have all done this before. When you put something into water, it pushes the water out of the way and takes its place. So what I'm showing here is a graduated cylinder, and the water's full up to about 150 milliliters. And the water's quite happy. And then you come along with this rock and you drop the rock into the water. Well, that rock is going to go to the bottom of the water, but where the rock is, the volume that the rock occupies, the water can't be there anymore. It pushes it out of the way. It has to, because the rock's there now, not the water. So as it pushes the water out of the way, the volume in this graduated cylinder rises. So you can see here, it was 150 milliliters before I put in the rock. I put in the rock and the level of the water went up because it pushed the water out of the way. And now it's reading 180 milliliters. That tells me that the volume of that rock is 30 milliliters. It's pushed 30 milliliters of water, that's a volume, out of the way. All right, so we say that that object has displaced the water. Instead of saying we pushed the water out of the way, we just use a fancy word, means displacement. It has displaced the water. In this case, it has displaced 30 milliliters of water, which means that its volume has to be 30 milliliters. So we can see an example of that. So again, now we're getting close to that bowling ball example. So remember, I said if we can understand the bowling ball, we'll understand the ship. So sink or float. So here we have like a garbage pail or a bucket full up with water. And we're going to dump a bowling ball into it. So the original line of the water was here. You put in the bowling ball, obviously the level of the water in that bucket rises. And the rule is if you completely submerge an object, the volume of water it displaces must equal the volume of that object. So here's this red bowling ball. It has a volume, which again is a physical size. It's the shape of that thing. It's got a physical volume of 4.5 liters. You put it in a bucket of water. It goes all the way to the bottom. It must displace 4.5 liters of water. It has to, because they occupy the same region of space. It's a purely geometric shape argument. All right, so 4.5 liters was the volume of the bowling ball. It'll push out it'll displace 4.5 liters of water from the space it used to occupy. That's very, very simple, okay? Now, the question of sinking or floating, here it comes. This is the key to the whole issue. If the mass, because remember, everything has mass and volume. If the mass of the object, which in this case is the red bowling ball, and in this case was 5.5 kilograms, if the mass of that object, which you can either measure or you get by multiplying a volume times its density, if that mass is greater than the mass of the water displaced, and remember, here comes what I asked you guys to remember before. Water has a special density of 1 kilogram per liter. So 4.5 liters of water, that's a volume, times 1 kilogram per liter, which is the density. I'm taking a volume times the density, gives that volume of water a mass of 4.5 kilograms. And if the mass of the thing you put in to push the water out of the way exceeds or is greater than the mass of the water that it pushed out of the way, that thing is going to sink. Conversely, if the mass of the object you put in, a same bowling ball, same volume, But what if that bowling ball only had a mass, of 4 kilograms, same shape, it's not as dense, so the mass is a little lower. If that mass of 4 kilograms was lower than the mass of water displaced, which in this example was 4.5 kilograms, that thing will float. Okay, that's what's giving rise to floating or sinking. What is the mass of the water pushed out of the way or displaced versus the mass of the thing which did that? And because that mass, sorry, I jumped ahead a little bit there, that mass here is always coming from the volume times the density, it really is just a question of density. It really is just a question of density because it's all about the mass, but the mass comes from volume times density. And since the volume is the same for the thing that goes into the water and the water, it's really just the density. So if you put something that has a density less than the density of water, it's lighter than water, and it will float. If you put in something that has a density of the object greater than the density of water, then that thing is going to sink. It's heavier than water. And if you put in something into water that has a density of the object that's exactly the same as the density of water, it neither floats nor sinks, and it'll just hang out there in the water exactly where you put it. So it won't rise and it won't fall in the water. It'll just stay at a certain level. So it comes down to a question of density. Is something less dense than water or more dense than water? More dense, sink, less dense, float. And the cool thing about that is we all know this if you've ever had ice cubes in your drink, and all of you have probably put ice cubes in a drink. Ice floats on the top. So if you haven't ever observed it before, do this for me, a little experiment next time. Get a nice clear glass of water so you can see the water. Just take one ice cube and put one ice cube in a glass of water. Does it sink or does it float? I guarantee you it'll float because ice floats. But does it float high up in the water? Or is it mostly down where most of it is underneath the water? Most of it is below the surface of the water, right? So when water freezes, it turns into ice. We know that. So ice is just frozen water, and ice has a density of 0.92, not 1.0. Water has a density of 1.0 kilogram per liter. Ice has a density of 0.92 kilogram per liter. So it's a little bit less. If it is less dense than water, it will float. But how close it is to being equal tells you how far down it'll go, right? So the density of ice at 0.92 is less than the density of water. It does float. But because the density of ice is 92% the density of water, one's 0.92, one's 1. So its density is 92% the density of water. 92% of it is below the surface of the water. And this is why there's a kind of a legend or a thing that people know that say when you see an iceberg, 90% of the iceberg is below the surface of the water. They always say that, like what sunk the Titanic. It's not the bit sticking out of the water that sinks ships. It's the bit under the water that sinks the ships, because 90% of the iceberg is actually under the surface of the water. It's actually 92%, and it comes just from the density here. But if you said something like 90%, that's absolutely fine, right? So that'll tell you how low or how high this thing floats in the water. So it all comes down to density. So now we can explain this famous picture, the blue floating bowling ball and the white sinking bowling ball. These two bowling balls have exactly the same size, the same volume, and they have to do that because when you go bowling, the ball goes down and it comes through the automatic returner and it comes on the machine and it rolls down. So they have to be the same diameter. They have to be the same size. That has to be allowed. So it's got to be the density and thus the mass of the ball that's different. And that is actually what's happening here. The white one has a greater density, which thus gives it a greater mass. And in fact, this white one is what we call in America a 12-pound bowling ball. Some people like heavier balls, some people like lighter balls. Kind of depends on how much upper body strength you have. This white one is a 12-pound bowling ball. It's a little bit higher, same shape, higher density, higher mass. And it sinks. The blue one, exact same shape, but it's actually a 10-pound ball. And they've achieved that by having a slightly lower density. And that gives it a total mass of mass when converted from its weight of 10 pounds to 10 pounds. So the density of the white ball, whatever it is, I don't know what it is, but it must be slightly larger than 1 kilogram per liter, which is the density of water, because it sinks. The density of the blue ball, whatever it is, I'm not quite sure what it is, but I know it must be slightly smaller than 1 kilogram per liter, and because it floats. And that's why I know I say it's slightly larger and slightly smaller, because it's right on the borderline. Those balls are not very different in their mass or their density, right? It's just a little bit of difference, but that difference makes all the difference in the world, and it makes the one float and the one sink. So they must be right around the density of water. The blue one's a little bit less and the white one's a little bit more, so it sinks. And that's what causes these things to sink or float. The other way to think about it, sometimes when you're working problems, when you get to like a university level, you will be solving problems related to this buoyancy thing, is you can calculate the mass of the water pushed out of the way. Well, because we know this is a 12-pound ball and this is a 10-pound ball, the mass of the water pushed out of the way by this white ball, when it's converted to a weight, must be between 10 and 12 pounds. Right? Because we know that the mass of the weight of that ball at 12 pounds is more than the weight of the water would be, and the weight of the blue ball at 10 pounds is less than the weight of that water would be. So however much the water weighs that got pushed out of the way, it's got to be between 10 and 12 pounds, because that's how floating and sinking works. All right, so now basically we have it. So now instead of 2 bowling balls, let us consider 2 things that have the same mass. So imagine a little toy ship. So I'm showing a steel ball down here and a steel ship right here. So they have the same mass. So imagine something that's like kind of heavy, right? Okay. And however much you want it to be. But imagine like you carried a brick or something. Imagine all that mass is in a steel ball, and you take that steel ball and you drop it into a tub, it's going to sink. Now you take that same mass and make it into a steel ship, but the ship is all hollow on the inside, right? Because you guys know what a ship is. A ship is not a solid metal ball. It makes no sense. You have to have room on the inside for the passengers and cargo to go. So that thing's going to have to be bigger, because it's not a solid thing. You need a space in the middle to load stuff in. That steel ship with the exact same mass, that is the same weight, will float. It's got the same mass as the ball, but it will float because it has to have a larger volume, because it's got this huge air gap in the middle. It's got to have the air gap because that's where you store your passengers or your cargo. And because its volume is bigger, but the mass is the same, its density has to be smaller so it can float. So here's really the explanation. We know now how buoyancy works. And the key point is for that, it's that empty cargo hold that's full of air that's critical. So when you see that 68,000-ton ship, if that was a solid metal block, it would sink right to the bottom of the sulacs. So buoyancy has nothing to do really with the shape of the boat. It has everything to do with that air gap in the middle. A ship is empty. That's the point. A solid metal sphere, no matter what shape you cut it, or no matter what its mass is, will always sink in water. There is no little metal, solid metal sphere that'll float, no matter its mass, no matter its size. But if you make it full of air in the middle, then it has the possibility of floating. So it's this empty cargo hold that's full of air that's critical. And here on the right, I'm showing a view graph of what a ship that's all full of air in the middle. It makes the whole density of the ship, even though the ship is huge, its density is still less than water because a lot of it is just empty air. And now you can see as you start to load down a cargo ship, like I'm showing on the left here, load it down with box after box after box of cargo. And now you can see it's starting to ride quite low in the water. Do you see over here where it's painted red? This gray line that separates the red from the blue is well above the level of the water. Over here, that gray line is now flush with the surface of the water. So as you load these ships up, yeah, they start to sink down. They start to displace water, which for most cargo ships, the amount of cargo they can hold is actually given in displacement. How much water does it displace as it goes down? It's another way of giving the mass that a ship can carry. It's a better way of indicating the mass that a ship can carry. So, and then of course, you could ask, oh, Dr. Rehse, if we just keep piling box after box after box on here, can you put on so much mass that the thing will go down and sink? Absolutely. Absolutely. You get rid of all the air pockets inside, fill it full of solid cargo gear, it will go down, right? So buoyancy isn't magic. Like I said, it's not the shape of the boat that keeps it up. It's just the total density has to be less than the density of water. So as I say here, although the ship is really, really heavy, and it has a lot of empty air in the middle. So the density of the ship is actually quite low, even though it looks huge. It's lower than the water, and that's what makes it float. And as the cargo hold fills up, that density rises, the ship will ride lower in the water. So check out this really cool picture that I saw. This is a brand new like super cruiser getting built. It'll be another cargo container, the Maersk Triple E. And you can see how big it is. You can see little people working on it here, and there's like people, guy up here standing on it. So you see how big the ship is. It's as tall as a 20-story building. Assembling this ship took about 250 workers. But they zoom in on it, and here it says the ship floats because the air inside its hull is less dense than the water inside. And if you can cut a ship in half, which ordinarily you can't do, but in this picture you can, you see it's actually mostly empty space. Sure, there's a lot of walls, and I'm sure there's bunk beds and kitchens and places to sleep and engines and turbines and all that stuff. But the inside is still mostly hollow, and it's full of air, and air is so much less dense than water. Air is what we call a gas. It has almost no density at all. There's no density to air at all. It's so much less dense than the water, and the ship is mostly full of air, that overall, on average, the density of that ship is less than the density of water. So even this 20-story tall ship can float along quite happily on the surface of the water. So put another way, in the case of our ship, the mass of the water displaced by the ship is approximately the mass of the water times the volume of the ship times 1 kilogram per liter. And you see how this does not depend on the mass of the ship. The mass of the water, which will determine whether the thing sinks or floats, is the volume of the ship times the density of water. It doesn't really depend on the mass of the ship. Once you have the volume of the ship, the shape of it, right, and how big it is and how much empty space there is, then you multiply that times the density of water, and that'll tell you how much water that displaces, and that tells you how much cargo capacity that ship can hold. And in this case, it can carry 68,000 tons of cargo capacity, which means the volume of the ship times 1 kilogram per liter would give you a mass of water of about 68,000 tons. 68,000 tons of water is pushed out of the way, so that's what can float on top of it. So this mass, when converted to a weight, must be greater than 68,000 tons. So thank you all for listening. I hope we learned a little something about buoyancy. Here's a great picture of the Paul R. Tregurtha from the Interlake Steamship Company, this beautiful, biggest ship to go through the Soo Locks. And here's a great picture of it. Next time you see those ships, I hope you get to see them on the Detroit River. So from where my office here in Windsor, I can look out my window, go down to the river. It's just a couple hundred feet away. I can see these giant cargo ships plying their trade up and down the Detroit River 24 hours a day, 365 days a year. And when you see those big ships and you say, gosh, how can something that big stay on the surface of the water? Now you're going to know, oh yeah, buoyancy, no matter how big it is, if the density of that thing is less than the density of the water, it can float. So it's not actually that complicated. That's what we love about physics. That's something that seems pretty complicated. No, it's not that complicated. It might not be very easy to see, but if you think about it for a little bit and try to talk about it with somebody, you'll be able to make it make some sense. And this buoyancy is just a great idea. So I hope that means something to everybody there. And I hope you all enjoyed listening to me. And I hope in the future, we have another interesting topic. We'll be meeting again sometime coming up in November. So thanks so much for tuning in to our Halloween special. And I look forward to talking with you all again next time real shortly. All right, everybody. Thanks so much.